Woo-hoo-hoo-hoo. New chapter, trig coming at you. But we got to get some of our basics down. A little bit of review first. We got degrees and radians. We got arc length. We got sector area. I mean, this is jam packed with a lot of fun here. But let's get started. Convert to radians or degrees. Now, do you remember how to do that? That is the question. Well, maybe we jot down a couple of formulas first. So to go from degrees to radians, I would multiply by pi over 180. All right. And then let's get a different color up here. To go from radians to degrees, I would multiply by 180 over pi. Oftentimes in radians, we see the pi in there, like you see in part B there. So I always think about like how, well, if I'm going from degrees to radians, I want to get that pi in there. So that's why the pi is in the numerator. And if I'm going from radians to degrees, I want to divide that pi out, which is why you see it in the denominator. That's how I think of it. But however you want to remember it is cool with me. So I got to go from degrees to radians. So I'm going to multiply this one. Maybe I'll go back to that purple. I'll go back to that purple. That'll be cool. I think it was that one. All right, so I'm going to multiply by pi over 180. So 120 divided by 180. I'm going to reduce that. I'm not using the calculator right now. 120 over 180 times pi. I can cancel out them zeros. Oh, love doing that. 12 over 18. That's going to give me 2/3 pi, or we'll say 2 pi over 3. Excellent. Wonderful. Next one. We've got 5 pi over 3. So I'm going to multiply this by pi, or 180 over pi. So my pi's are going to cancel. And what I'm going to do to make this a little bit easier without a calculator, rather than multiplying by 5 by 180, because that's going to be really large, how about 180 divided by 3 first? That's going to be, 60? Yeah. So I've got 5 times 60, which is then just going to be 300. Awesome. Next part. Find the missing side of each triangle. Now, if you had me for honors geometry, I'll be very disappointed if you don't remember this. These are the wonderful Pythagorean triples that we got going on. We have a 3, 4, 5 triangle, a 5, 12, 13 triangle, and an 8, 15, 17 triangle. One last one that's not on here. I'm going to just throw it in here off to the side. We've got ourselves a 7, 24, 25. Make sure you have these jotted down. They are going to come up in the next lesson a little bit more. You're going to see them sprinkled throughout the trig chapter. Knowing those 4 triples will be super duper helpful. So our objectives, once again, we've got convert between radians and degrees. We already did that. Boom. Check. We'll have a little more practice with that. Identify coterminal angles. We haven't done that yet. Arc length, sector area. Okay, so we got one of them done. Let's keep going. So how do we measure angles? Again, a lot of this is going to be review, but it doesn't hurt to go back over it before we start getting into the more complicated stuff. So our initial side, that's going to be our positive x-axis, okay? Positive x-axis to our terminal side of the angle. So it's an angle of rotation, okay? So we're going counterclockwise for a positive angle. This vertex right here, when we're dealing with this as angles of rotation, that's going to be my origin. So you could almost think of, you got your y-axis. That was that's a little better. And we've got our x, positive x-axis there. It's already labeled. We're good to go. So that's my origin, where that's going to be. All right, wonderful. Now, a negative angle is just going to start going down. So from that positive x-axis, it starts rotating that way first. Right? There we go. Instead of going counterclockwise, it goes clockwise, starting from that positive x-axis. Now, one thing I want you to pay attention there is how we call that the terminal side. That'll come up with coterminal angles. But before getting to coterminal angles, let's think about what the heck is a radian. What does this all mean? Well, if we travel around the circle one time, okay, one time, circumference is our 2 pi r. right? Now, for a radian, we're using a unit circle with a radius of 1. Okay, so if my radius is 1, then my circumference of that circle, as you can see here, we substitute in 1 for the radius, we would get 2 pi. So 2 pi is a full rotation around a circle of the full circumference of a circle with a radius of 1. So we have the 2 pi is equal to 360 because 360 is a full rotation in degrees. 2 pi is a full rotation in radians because radians, we're assuming the unit circle a radius of 1. And another important part to jot down, it's hard to see that orange there. So let's go with maybe green. I don't know why I'm circling it. It's already in a red heart. Isn't it already noticed enough? Okay. So 2 pi equals 360. Pi equals 180. So a little bit more detail about a radian now that we've got the general idea there is that, so if my radius is 1, so I'm going to say this point is, if we're on the XY coordinate plane, we got my origin. This is going to be the point 1, 0. So it's a radius of 1, right? Well, if I travel halfway, let's see here. If we go halfway around the circle, down to there, how far have I traveled? Well, let's see here. That's going to be half of the circle, right? Well, my full circumference is going to be 2 pi times my radius of 1, which is going to be 2 pi. And if I only go halfway around, that's only going to be pi. Well, what if I go a quarter of the way, right? So that would mean that I'm doing 2 pi divided by 4. All right, so I'm going to have pi over 2 for a quarter of the way around the circle, which would land me, I'll go in a different color now, go light blue. So pi over 2 is going to land me right there. Okay, it's just the distance that we're traveling around that unit circle. And we can go into 60 degrees, 45 degrees, so on and so forth. We'll get to more of that in a little bit. But again, a radian is just that portion of the circumference of that unit circle. So what are coterminal angles? All right, we talked about the terminal side, then we were talking about what are coterminal angles. So coterminal angles are just, if I have an angle, say, of like 20, it's just another angle that has the same terminal side. Okay, so if we're starting from that positive x-axis, it lands in the same spot is one way to think of it. So if this angle that I have here is 20, what would a coterminal angle be? Well, if I do a negative rotation, how many degrees would that be? Well, if it's 360 to get all the way around, then I would just need to go negative 340 to get over to that. Or I could go in the positive direction even. So I could go like this. I've gone 360 and then another 20. So this red one would end up being 360 plus 20, which is 380 degrees. Both of those would be coterminal to 20 degrees. All right. So what are coterminals? They share that terminal side. They have the same terminal side as the angle. In other words, we can basically just add or subtract 360 to the angle that we have. All right. So I would jot that down. You can add or subtract 360 to the existing angle. Or what's the equivalent of 360? If we're in radians, you can just add or subtract 2 pi. That's awesome. Fantastic. Now, with coterminal angles, sometimes they'll give you restrictions. Sometimes they'll say something like this: what's the coterminal angle A or a coterminal angle to 20 if we're between negative 360 and positive 360? And they'll leave one of them bounded, one of them unbounded. So what would that be? Well, 380 would fall out of that, so I couldn't use 380. So in this case, 340 would be the only one that would work. I would have needed to subtract 360 from 20 to get that one. So that's why we have the add or subtract. They're both coterminal angles, but only one of those fits within that realm right there. And that's what we'll usually do on those types of problems, so that we have one correct answer and not an infinite number of correct answers. Who wants that? All right, some examples with this now. Given the angle 135 degrees, draw the angle of rotation, find a coterminal angle, and convert to radians. So this one we didn't restrict what your coterminal angle could be. So there's an infinite number of them, but I'm just going to give you one. All right, so first let's go ahead and draw this thing. I'll keep it red. 135 degrees. Where's that going to land? Well, that's going to be in my second quadrant right there. That's 135 degrees. Cool. Now, something we'll get to later, reference angle. Remember reference angles? I'm gonna pepper it in here. Reference angles where you go to your x-axis. My reference would be to go halfway is 180. So my reference, this would be 45 here. Ooh, it's a little preview, also a review, but a preview of the next lesson here before we can get there. All right, so we got our angle. Let's find a coterminal angle. Since we're in degrees, I can add or subtract 360. I'll go ahead and add 360. So 135 plus 360, that's a 0. What's that going to give me? That's going to give me 495. Boom. There we go. That's a coterminal angle. It didn't say that I had to be between. It didn't give me any restrictions there, so dealer's choice. And the last thing, convert to radians. So I'm in degrees. I'm going to go 135, and I'm going to multiply that by pi over 180 to convert into radians. And that looks almost like a 6, 180. There we go. So I'm going to reduce this, which is a little bit tricky, but we end up getting 135 over 180 is 3/4, so we're going to have 3 pi over 4. And you may even remember some of that from your unit circle from last year of that 135 is your 3 pi over 4. All right. Oh, man, now we're in radians. Yikes. And it's negative. What are we, crazy? Okay, so I'm going to see if I can. There we go. There's a graph. Let's draw that bad boy as our angle of rotation here. And I'm going to mark out a couple things for you guys. I think that might help. I'd have 0. I have, this is pi over 2. This is 2 pi. Or sorry, not 2 pi. Just pi. This is 3 pi over 2. And then we're back to 2 pi over here because that's the full rotation, the full 360, right? Okay, so where is my negative 2 pi over 3 going to land? Well, for that one, I'll change colors here. We'll go with blue. I'm going to end up in the third quadrant like that. Negative 2 pi over 3. If you think about 2 pi over 3, that's a little bit bigger than like 1/2 pi. So if I was positive, I'd be going into the second quadrant, but because I'm negative, I'm going into the third quadrant. Lovely. Now, the next thing is find a coterminal angle. So remember, I can just add or subtract 2 pi. I'm going to add 2 pi. I'd rather add if it doesn't tell me restrictions. I'm just going to go ahead and add. So if I take negative 2 pi divided by 3 and I add 2 pi, I need a common denominator, don't I? I'll show a little bit of work. So negative 2 pi over 3 plus, well, how can I make 2 pi into something over 3? Well, that'd be 6 pi over 3 because 6 over 3 is 2, right? Okay, woo, fractions. If you are struggling with finding a common denominator of fractions, I don't remember what grade level they cover that in, but you could maybe ask a younger sibling or a friend that has a younger sibling, and they'll help you out on those fractions because we tend to avoid those, right? That was a voice crack. I deserve it for making that joke. Okay, we're leaving it in. Let's go. So I've got negative 2 plus 6 is 4 pi divided by 3. There is a coterminal angle. That's actually between 0 and 2 pi. So if there was that restriction between 0 and 2 pi or negative 2 pi and 2 pi, we would have fit that description, that restriction there. Awesome. Last thing, convert to degrees. Okay, so that means I'm going to multiply negative 2 pi divided by 3. I'm going to multiply that by 180 divided by pi. So my pi's are going to cancel. That will reduce. The 180 over 3 reduces down to 60. So I just have, let's see here. I guess I could reduce that on there. This becomes 60. So then I'd have negative 2 times 60 is negative 120 degrees. Awesome sauce. Fantastic. Whew. Man, I'm out of breath here. We're just going for it. So remember when I said oftentimes we see pi when it's radians, but it doesn't have to have pi when it's radians? Here we go. 2.2 radians. We're going to convert that into degrees to the nearest thousandth of a degree. That's 3 decimal places. Trace. So I will have 2.2 multiplied by 180 divided by pi. And we can just plug all of that into our calculator. So my calculator told me, and I'm going to go with squiggly, because it's approximately, 126.0507. So that would be a 1 degrees, 3 decimal places. Good stuff. Don't you dare use 3.14 for pi. We use the pi button. All right. It's adult calculating right there. You are young adults. Use that pi button. All right, time for arc length and sector area. That S is not like possible extra arc lengths. It is the variable often used for arc length. So arc length is often used as a lowercase s. You may see that, jot that down. So let's start with arc length here. So arc length is just a portion of our circle's circumference, right? And if we think back to radians, our 2 pi that's all the way around, right? 1 full revolution of the unit circle, right? And then anything else beyond that is just really an arc length of the unit circle. So we can expand that upon a whole lot. So an arc length is just a portion of our circumference. So let's start with if theta is in degrees, and then we'll also work with radians. Okay. Well, what do we know about circumference? Well, circumference is. Oh, let me change colors there real quick. I'll go with purple. So circumference is equal to 2 pi r, or pi times diameter, right? And arc length is just a portion of that circumference. And if you know the angle measure, which is out of 360, this is starting to sound like we could set up a proportion for this, right? So if my central angle is theta and going all the way around is 360, then I can find my arc length, which is S, over my total circumference of 2 pi r. There we go. So whether I'm given a central angle or I'm given a radius, I can find the arc length. If I'm given the arc length and the radius, I can find the central angle. Anytime I'm given 2 out of those 3, I can find the other one. Now, some people like to multiply this out and solve for S, solve for your arc length, but I feel like that could be counterproductive if we ask other questions. So I like to leave it as the proportion. You may see them written out in different ways. Okay, so that's for degrees. Now, what about if we're in radians? I'll go ahead and switch colors. Well, if 1 full revolution for radians is 2 pi, right? Because 2 pi is equivalent to 360. All I need to do is swap out the 360 for 2 pi, and the formula is exactly the same. So whether I'm given radians or degrees, I can use either one, pretty easily with this wonderful proportion that we have set up for arc length. Awesome. That's pretty good. Now, how about sector area? For sector area, well, sector area is a portion of the area of a circle. Well, what is the formula for the area of a circle? Area of a circle is equal to pi r squared. So if the full circle is 360, and I just want a portion of it, whatever that might be, I once again can set up the same type of proportion. I can take my central angle divided by 360 and set it equal to the portion of the circle, or the area that I want, the portion of the circle that I want. So the sector area divided by the area of my total circle. So now, once again, whether I'm given a central angle and a radius, or a sector area and a central angle and try to find the radius, I can get any one of those things given the other two, and we can throw any type of problem like that at you. So this is for our degrees. Once again, we can switch this out for radians. I will have theta divided by 2 pi is equal to the same thing, sector area divided by pi r squared. And you will often see various formulas for this one here already solved for you. And I'll jot those down real quick. So one that you might see pop up would be 1/2 pi r squared theta for your sector area. All I did was just cross multiply and solve for your sector area. You can do the same type of thing for arc length. And that one actually works out real nice. It's just S equals R theta. Your arc length equals R theta. And once again, that happens from cross multiplying and solving. So when you cross multiply and solve, when you divide by 2 pi, those cancel out and you're just left with R theta. So a nice, real clean formula for that one, but only when it's in radians for those. I personally like the proportions because it makes sense to me to set up a proportion, and proportions are so useful in so many different areas. And it's not one formula to remember. I don't have to, if I was given the sector area and I was asked to solve for the radius given theta, given my central angle. That's kind of a pain to then unsolve that one and work with it. It's just easier to cross multiply in each situation. But totally up to you. However you want to work it, I like to provide multiple ways for you. All right, it's time for some arc length application. So that's Eratosthenes. All right. Man, they had some cool names back then. Now, here's the thing. I was blown away with this when I first started. I remember hearing this years ago, and it was like really fascinating to me. So if this does not blow you away, then I don't know what's going to excite you in this math class. All right, so he used a couple sticks and the sun's shadows on the summer solstice to figure out the Earth's circumference. How the heck did he do that? Well, here's what happens. So he was hanging out in Alexandria, right? And on the summer solstice, he saw a shadow cast by some of the buildings, okay? But heard that in nearby Syene, okay, which I think is now Egypt, heard there was no shadow. He's like, well, how the heck does that happen? How is there a shadow here on the same day, same time, but there isn't one elsewhere? So he thought to himself, well, the Earth has to be curved, okay? So this is not fact yet. We don't have satellites at this time. We can't see this. But he had a pretty darn good hunch that the Earth was then going to be curved. And he thought, hey, perhaps I could figure out the total distance around the Earth, the circumference of the Earth, using these shadows and a known distance. Okay? So what he did is he had a dude go from Alexandria to Syene. There's actually one less E in there. Good thing it doesn't exist, I don't think, anymore, because it's Egypt, I believe. So he had a guy go from Alexandria to Syene and found that distance, like he had the dude pace it out, okay? He paid a guy to walk and pace it out, and it was 8,000 kilometers, because everybody uses kilometers but us. Okay, they use the metric system. So it's 8,000 kilometers. Now, the other thing that he did is he popped a stick in the ground, okay, and then measured the degree of the shadow. So when we're talking about the Earth, when you're like a space, like it's relatively flat because it's so big and round. But what he did is he measured that shadow, and I'll come in, with some nice sun rays here. And here's the thing is the rays come in from the sun. They don't go out like this. They come in parallel because that distance from us to the sun is so far that those rays are coming in parallel. So the shadow created in Syene and Alexandria, if the Earth were flat, sorry if you're a flat earther, if the Earth were flat, would be the same then because the rays are coming in parallel, but they were different. So those rays came in, and what happened is we had this angle here of roughly 7.2 degrees. Okay. I don't know how he measured that. I'm guessing maybe a protractor or something like that. I mean, they knew what circles were, so they could, divide that by 360 and mark it all out. That might have been how they did that. I don't know if Trig was around at this point in time because he could have measured some sides and then used inverse trig, but I don't know if that existed yet. Anyways, it got that 7.2 degrees somehow. Okay, so what do we do with that? What did he do with that? Well, 7.2 out of 360 is roughly 1 over 50. All right, so 7.2 divided by 360, that is 1 over 50. Okay, so let's remember that for a sec. Now, one last thing that I want to pop in here for a picture is if we're thinking about this as a circle, the Earth, okay, and you've got, say, Alexandria here and Syene here, and if you were to extend that shadow back in and back in, what you end up getting is that 7.2 degree angle, okay, central angle essentially, to the Earth's core, the center of the Earth, all right? So what we're talking about here is, and we know this distance is 8,000. That's essentially my arc length of this circle, the circumference of the Earth. So what he did is he set up a proportion just like we have here in our class, where he did the 7.2 out of the total 360 degrees of a circle. He knew that the distance was the 8,000 kilometers, but didn't know what the circumference of the Earth was. The circumference was not known. The radius was not known. He didn't have a tape measure to go to the core of the Earth to find out the radius of the Earth, right? He only had the arc length and that angle that shadow made, which would then correspond to that central angle of this great circle that goes around the Earth. So he did a little bit of cross multiplication. We know that that reduces to 1/50th. We already did that. And then 8,000 multiplied by 50, that's going to be 40,000 kilometers is equal to the circumference, that was me, of the Earth. Whew. Oh man, I thought this thing crashed for a sec. I just Googled, using the Google Internet machine, the circumference of the Earth. I'm on the computer here, and it is 40,075 kilometers. That's the actual. And this guy with some sticks and some other buddy of his that he paid to walk 8,000 kilometers to a neighboring city, Syene, figured out with that minor error what the circumference of the Earth was. No GPS satellites, nothing like that. Again, if that doesn't blow your mind, I don't know what will. Okay, but I hope something else. I hope we find something else that blows your mind, because that was incredible. All right, let's keep going. All right, here we go. We got Drake. Drake is back. As you know, he's a rising star in the Huntley Farmers Market game, right? He started from the bottom. Now he's roughly here. He plans to plant a new circular garden at his house, switching it up from the rectangles and things, and section it off into 3 pieces. Okay, look like a pie chart of garden. So he busts out his protractor and plans to use 100 degrees for tomatoes, 150 degrees of that circular garden for peppers, and the remaining for herbs and spices. If the diameter of his garden is 40 feet, how much area does he have for each section? So let's go ahead and draw this up. Actually, I want to leave Drake in there, so I'll just scooch over to the side a little bit, maybe a little zoomy out. Okay, so if I've got this circular garden here, that's a nice circle, and we know it's a diameter of 40. We'll keep that in mind. Now I said 150 degrees, or 100 degrees was for tomatoes, 150 for peppers. Well, I like this, looks about like 150, not quite 180, right? So we'll call this peppers. A bit beyond 90 is the 100, so we'll call that our tomatoes. And then lastly, the herbs and spices. Cool. And I'm going to put in, I should really say, the 150 degrees, 100 degrees, and the whatever that would be what? 110? Yeah. So we subtract the other 2 from 360. All right, and my radius, well, if my diameter is 40, then my radius has to be, it's going to be 20, and we're going in feet. Okay. Drake lives in America. We use the standard rather than the metric like Eratosthenes was using. Okay. So what can I do here? I want to find the area. How much does he have for each section? Well, this, we're dealing with sector area. So if I were to take my super awesome proportion, right? And let's find peppers first. So we'll do peppers in, we'll go green because they start green and then they turn red or orange or yellow, pending your variety that you have. Fun fact. They don't just grow that color. All right, peppers. So I would have 150 out of 360, 150 out of the 360 is going to be peppers. And I know that my area is pi times my radius of 20 squared. And I want to know what that sector area is. I'll just call that A. So I can cross multiply and solve. Let's do that. All right, so once I do that here, I've got, when I multiply 20 squared by 150, I get 20 squared times 150 gives me 60,000. Keep the pi there, equals 360 times A. And I'll divide by 360. And at this point in time, I'm going to end up getting fractions, but because this is an application problem, I'm going to go with the decimal. So I'm going to multiply everything out, 60,000 divided by 360 multiplied by pi, and my area ends up being, let's go to 3 decimal places here, 523.5987, so, 0.600. Can you hear Jenny howling out there right now? There's some sirens going by, and Jenny is howling up a storm. And don't forget our units. This is feet squared. Nice. Okay. It's always weird when you got those. You got a round. Or wait. What am I thinking there? I don't need a round. It's 5987, so 599. I was thinking it was 5997. My apologies. I don't know what I was thinking. I was focusing on Jenny howling. All right, there's the peppers. Now let's go on to our tomatoes. We'll go red for tomatoes. Although they do start out green as well. I'll go red because we already used green. All right, tomatoes. Same idea here, except for now, my central angle is 100 degrees. So 100 divided by 360 is equal to my area of that sector over pi times 20 squared. All right, why don't you pause the video, try it, and then see if you got the right answer. And there we have it. We have 349.066 feet squared. Always make sure when you guys are typing these in the calculator that your final answers do make sense. I was typing mine in and I forgot to square the 20, and I ended up getting some answer like only 17 feet squared. And I was like, that doesn't seem right. So always make sure your answers do make sense here, and they agree with one another to make sure you can catch some little mistakes. All right, for the next one, the herbs and spices, I'm going to let you guys set this one up on your own and solve it. So pause the video, try that, and then you'll see the answer pop up here momentarily. Did you pause it? Okay. And there we have it, 383.972 feet squared. Whew. Nice. Very, very wonderful. All right. We got two last problems here, guys. I know it's getting a little lengthy, but you're doing an excellent job hanging in there. So this one here, given an arc length. Look at that. Like I've been foreshadowing here, much like a good movie or film would. If given an arc length of 15 over 2 pi feet and a central angle of 3 pi over 4 radians, find the radius of the circle. Well, this is our arc length. So we have, it's going to look a little messy here. It's going to look a little messy. But if I plug this into my proportion with 2 pi over here, my circumference is 2 pi r, right? And we have an arc length, which would go over here, 15 over 2 pi. And this is going to be 3 over 4 pi or 3 pi over 4. I'll go like this to match the other one. Woo! That's a lot going on there. But I'm seeing something right away here that might be nice to do. Why don't I cancel out my pi's? As much as I love pi, we got them in numerators and denominators all over the place. Why not just get rid of them? Okay, cool. So now I can cross multiply. I can simplify a little more if you'd like. I'm just going to go for the cross multiplication here. So I've got 3 over 4 times 2r. That'd be 6 over 4. Yep, cool, awesome. And I can reduce that to 3 over 2. Why don't I do that? Lovely. And then that equals, and then we have 15 over 2 times 2. Well, that's just going to reduce down to 15. And then I'm going to divide by 3 over 2, which is the same as multiplying by the reciprocal of 2 over 3. And when I reduce that, 15 over 3 gives me 5. 5 times 2 is 10, so I have a radius of 10 feet. Got scared for a second there with all those fractions and fractions on fractions, right? Like stacks on stacks. But the math way of doing things, fractions on fractions. Not too bad though. Uno más. So here we're given a sector area of 22 pi centimeters squared, and a central angle of 220 degrees. Okay, we're back in degrees. Find the radius. So notice how I didn't convert the last one into degrees just because I feel more warm and cozy about degrees than I do on radians. I can just use the 2 pi instead of 360 and vice versa. So be comfortable working with either one. I think you guys can handle it. I believe in you. Well, now what I've got is my angle is 220 divided by the overall 360 degrees of a circle is equal to, I know my sector area, so that's 22 pi up here, and I don't know, not 2 pi, my goodness, we're in area now, pi r squared. Okay. Cool. Well, how about this? I'm going to start with just canceling these pi's here. Boom, boom, gone. Less to worry about. And now I will go ahead and how about I reduce this as well, actually. Boom. Cancel out some zeros. 22 and 36 are both divisible by 2, which would give me 11 and 18. So that makes my numbers a little more manageable. That's wonderful. And now I can go ahead and multiply 18 times 22. I don't want to make a mistake. I got my TID4 right here. What's up? Yo-ro. And I get 396 equals 11r squared. And if I divide by 11, I should get 36. Yep. So r squared is equal to 36. And if I take the square root on both sides, I get r equals plus or minus 6. But because this is an application with circles, we're just going to go with the positive radius. We're not going to have a negative radius here. Not in this case. Awesome. And that's centimeters. Gotta love those units. Woo! I need a drink of water here. That was some good stuff. Thank you guys so much for hanging in there. You're fantastic, wonderful. I hope you guys enjoyed it as much as I did, especially the Aristoteles problem where he found out the circumference of the Earth. That was incredible. I love it. America, freedom, rock and roll, Costco, Riverdog Jenny on the gram.